Hello everyone, so today we're going to prove that 1 plus 2 plus 2 squared plus dot 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 2 to the n minus 1 equals 2 to the n minus 1 for n greater than or equal to 1, essentially all the positive integers here, okay? And we're going to be using mathematical induction. We have two types of mathematical induction, like the regular one, as I like to say, just plain old mathematical induction. Then we have one that's what we call strong induction, which we won't be speaking of today. So the way it works when you're doing working with mathematical induction, you want to work with a proposition, okay? And we're gonna call that proposition, we're gonna abbreviate it. So that's where I have let P of K. P of K is our proposition, and the proposition is that 1 plus 2 plus 2 squared plus 2 to the k minus 1 equals 2k minus 1. That's essentially what we're trying to prove. And the way mathematical induction works, it's like, you might have seen this before in your classes, but I'm going to say it again because I think it's a pretty good analogy. So imagine you have a row of dominoes here and they're all like stacked right next to each other. And the idea is like, well, if one falls, the next one falls, and et cetera, goes on forever, okay? And a couple things that need to happen here. The first thing is that when you need to make sure that the first domino falls in order for this whole process to start. So that's what the P of 1 stands for. So we want to make sure that my domino falls, so my first case is true. And the other thing that we have to make sure is this, is that if you know that one of the statements is true for one integer, then it should imply that the next one is true. So another way of looking at it with the dominoes is like, if you take any integer along the line, and if that one falls, can you make sure that guarantees that the next one falls, okay? So that's what mathematical induction involves here. And the base case here is what gets things going here. That's P of 1 here in this case is true. Yeah, the value here, it's 1 because I'm starting with 1. Sometimes it's 0, sometimes it could be 2, it could be really anything. So I want to show that the statement is true when I plug 1 into it. So if you plug 1 into it, you would get 2 to the 1 minus 1, or 2 to the 0, which is 1. And the next one would be 2 to the first minus 1, which is 2 minus 1, 1. Okay, and both these sides of the equation are true, so the statement holds for when 1 is true. Now we have what we call the inductive step. So when you're doing mathematical induction, you have a base case and you have an inductive step. And the inductive step says if P of K is true, then P of K is 1 is true as well. Or with logical implications, P of K implies P of K plus 1. Okay, so all I'm saying here is like, yeah, if my statement holds for one value for positive integer, I want to show that it holds for the next one as well. Okay, and this part typically is like the harder part. It's the one that requires most of the work and a little bit of ingenuity on our part. So we're going to assume that the statement P of K is true. So this statement 1 plus 2 plus 2 squared plus da 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 plus 2 to the k minus 1 equals 2 to the k minus 1 holds for some k greater than or equal to 1. I'm not saying all k, I'm just saying for 1, okay? And what I need to show is the P of K plus 1 statement is true. So P of K plus 1 basically is the statement with like the next value. And in terms of a formula, you think about it, a formula, you could take the statement that I had up here and replace the k's with k plus 1. Now, that's not always that easy, but in this case, it's going to be along those lines, okay? Now, how do we do this? Well, let's take the 1 plus 2 plus 2 squared plus 2 to the k. And if we look at that, that is actually like saying 1 plus 2 plus 2 squared plus da 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 2 to the k minus 1 plus 2 to the k. Yeah, because when that statement 1 plus 2 plus 2 squared plus 2 to the k means you're adding up all the powers of 2, including 1 itself is 2 to the 0. up to k, so k minus 1 would be in there. And the reason I wrote it out this way is that this is my P of k statement pretty much. All of that, we were told, is equals 2 to the k minus 1, okay? So all of that gets replaced by that. And that often you will do. You will take your inductive step, somewhere in your inductive step, you'll use the fact that P of k is true, and you'll use that by doing like a replacement like I did here, like a substitution, All right, and if you notice now, I have two to the k's. In other words, 2 times 2 to the k. I'm going to add those together, and this is where I said a little bit of ingenuity is needed. You need to use a little bit of algebra a lot of the time, or rearrange things, etc., or rewrite something. And 2 times 2 to the k is like saying 2 to the k plus 1 minus 1. And we have reached the conclusion we needed. Yeah, you just use properties of exponents. 2 times 2 to the k. 2 is like saying 2 to the first, so you add the 1 and the k together, 2 to the k plus 1 minus 1. Okay? All right, so we have proven that, let me just write this down, we have proved that if P of k is true, then P of k plus 1 is true as well. And my conclusion will now be this: therefore, 1 plus 2 plus dot 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 2 to the n minus 1 equals 2 to the n minus 1 for all integers and greater than or equal to 1. Okay. Yeah, why is this? Why am I saying that it's true for all integers now? Well, because since I know the first, when I proved P of 1 was true, the first case was true, and that from what I just did right now with my showing that if P of k is true, then P of k plus 1 is true, that means that if P of 1 is true, then the next statement is going to be true, which would be P of 2. And again, since P of 2 is true, then P of 3 is true, and etc. It goes down the line. So this is true for all integers, okay? And again, why is that? Because if I proved, when I said P of k is true, I'm saying that the statement is true for a value of k. K could be pretty much any positive integer. And this applies P of k plus 1 is true, okay? All right, so I hope this helps, and we will probably be doing a video on something else where you can use mathematical induction and other, because there's several problems out there and many ways of using this, and maybe a strong induction video as well in the future. All right, well, thank you for your time.